Everybody, can you hear me well? All right, hello. My name is Alex. I'm a long-term Haskell enthusiast. I've left research a while ago. I've been focusing on practical applications since then. I'm working for PricewaterhouseCoopers Switzerland, and among other things, I've been doing research and development projects like this one we're presenting today. With me is Richard.
Hi, everyone. I just want to highlight this work was done as part of my work with Tweeg. Jane Street is paying for me to be here at the conference. That's why they both get there on the slide.
Right, fantastic. Thank you, Richard. So we're going to present together. I'll start first. So Eiger is the name of our regulation as code framework. It is named after a famous mountain in Switzerland because we're not very creative with names, I guess. But it gives us audible, flexible, executable legal requirements. I'm going to explain later what exactly this means. So it's important to understand this is not a scientific publication, but it's a demo of an application of Haskell that solves an important problem in society. So roughly, we're going to talk about the problem and the solution we're presenting. We're going to give a short demo of the code in action. Then Richard's going to explain the magicianry behind the scenes that he made possible. And then we have some time for questions. All right, so what is this about? So this topic may sound boring, and to some extent it is, but regulations are underpinning much of how the business and the society of the world works. So as the world is getting increasingly complex, so are regulations get, and the old ways of delivering on them is really reaching their limits. So, for example, a client may wonder, so what regulations are coming up? Which regulations apply to me? There are lots of rules, exclusions, whatever. What are the details of the legal text? How do I ensure I'm compliant? Because usually there comes punishment if you're not compliant. So you need to make sure you're compliant. How do I keep the risks and foremost the costs low? Because typically being compliant is not a competitive advantage. It's just a must-have. So you need to keep costs low. And how do I monitor the changes over time? These are typically the questions a client may ask. We chose one example, the carbon border adjustment mechanism. It's a European regulation that requires businesses based in the European Union to report and financially offset carbon-intensive imports from non-EU suppliers. This is coming in force next year, January. So a client may go like, uh-oh, that's not a lot of time. I've never heard of this before. What am I supposed to do? It talks about the product coverage of carbon-intensive products. So what does carbon intensive mean? Which products are included? Am I affected? How much am I affected? It talks about direct and indirect emissions. So the client wonders, what's the difference? Is this relevant for me? It talks about the geographic coverage that includes all non-EU suppliers. So it goes like, okay, well, I'm importing a lot of stuff from outside of the EU, so I guess I'm affected. And it talks about sanctions. So the client goes like, oh, I want to avoid that. So they pick up the phone and they call a consultant to help them navigate this. This is a very typical business case for a firm like PricewaterhouseCoopers. So far, this is how this has been solved. So there's a regulation coming. Let's say it's a PDF file from the regulator. And then somebody from our experts sits down and reads it through and talks to other experts and forms an opinion about interpretation. Maybe there's clarification required, so they go back and forth and they form an understanding of what this regulation means and how it's supposed to work. They create secondary literature, some Word documents, something like that, where they explain their understanding of how this whole thing works. Okay. Then there's a client who needs help. So there's an engagement manager helping the client. He takes the literature from the lawyers and translates them into a PowerPoint deck, usually explaining for the client specifically what is relevant for you. Okay. Then during the engagement, somebody, typically in this case, in the CBAM example, as a supply chain expert, needs to source the data. We need to feed into the machinery to calculate the numbers and see, for example, how much offset do I have to pay. So they would go out and try to find the data somehow and make it match to what they understand is required from the PowerPoint slide. Then they present the data, let's say in an Excel sheet or something like that. It's not uncommon. And then there's a data analyst who runs them through tools like Alteryx, which is like, let's say Excel on steroids, really. And on Power BI, which allows you to create reports. So they deliver the numbers, they show it to the client, and their client's accountant goes and takes it into account for the budgeting, for example. That's a very typical cycle. It used to work really well, but this approach is struggling to scale and keep up with the increasing complexity and volume of regulations. It's very manual. And at every step, you have a breakage between the medium you're using. You go from PDFs to Word files to PowerPoint slides to Excel files. And at every step, mistakes happen. So it's costly. It takes a lot of time. The quality sometimes is not what it's supposed to be. We need another round to get to where it needs to be. So you can imagine. There's almost no automation here. So we changed that through Eiger. So at the beginning, again, the regulator publishes the regulation, but now we pair a software engineer with a lawyer, and they pair program the regulation in Eiger. Sounds crazy, but it works. We've tried it. At least anecdotally, it works. So the reason why this works well, this is the key insight. Lawyers are very much used to work with Excel, and Excel formulas are pure functions. So in a sense, they already are software engineers. They don't know it. And they don't deal with a lot of the plumbing we need to deal with. But that's where we come in. So we pair with them. We took good care to make Eiger code, which is Haskell code. It's not an embedded language or anything like that. It is Haskell code. But we took good care to make it look like Excel-ish. A little bit more on steroids maybe again. But plus some basic SQL. And there's a lot of plumbing, not a lot, but some plumbing, and I tell the lawyer, don't worry, I'll take care of this. It's a very practical approach to this whole situation, but it works really well, we found. So we produce Eiger code, and that code is going to be used and reused throughout the whole cycle. So we may write another Word document to explain the general structure, the design, some things that are important, like you would document any source code, really. You may still create PowerPoint slides because clients just like PowerPoint slides a lot. So it's a nice way to present things. But you would always refer back to the code, to the actual source of truth. When you source the data, you can use the schema defined in the Eiger code. So there's less chance that you provide the wrong data or misleading data. We can then actually run the Eiger implementation based on real code, real data coming from the client, and create the insights we need. So that's pretty much the solution to the problem we propose. So the Eiger model is simple because we have to keep things simple, but it's still, I think, powerful enough. So this is a graph of a dependency graph of facts. So facts are the little dots. A fact is a single value, such as a monetary value, a Boolean value, a percentage, some domain-specific classification, whatever you want, right? So if you have facts, you can define rules that define how one fact is being determined based on other facts. That's pretty much what the regulations are structured like already. So there's some translation required, but it's very close. So all regulations that judge the merit of a case based on facts are applicable here. Some facts are required as input. There's no way to derive them. You could maybe later keep deriving, so it's very extensible. So for now, you say, I need this as an input. Tomorrow, you actually implement the logic behind this fact. You can be very, very flexible with this. All facts can be queried as output. So I'm wondering, given this Eiger model, given this data, what is a tax owed? Or something like that. You can ask different questions to the system. And you can override all facts with input values to run simulations. So if you have an input value, the Eiger framework would not execute the rule, but just take it at plain face. So that's the model. It's very simple, but it's powerful enough to model all the regulations we've tried so far, at least. Now, if you look at the benefits, we computer scientists, we go like, yeah, sure, we have, this is what you get from software. But the point is, for the consulting business, this is all new. So our main contribution is to bring those benefits to the consulting business. So, for example, we have precision through the formal encoding. We get disambiguation. It's a huge problem in reality. Humans trying to write text that is consistent is just a hard problem, particularly if it becomes like 50 or hundreds of pages and 20 working groups and everybody's kind of chiming in. It very quickly becomes inconsistent. You have contradictions, you have gaps. This is a real problem. And that has a lot of downstream costs, because every time there's an ambiguity, you may choose one interpretation, but the judge may choose another one. So you have a lot of conflict, legal arguments, stuff like that, all coming from that. So we close that gap. It's complete. We can, think about corner cases. As an engineer, while you write code, you immediately are forced to think about corner cases. So I ask immediately the lawyer, hey, what about this situation? He goes like, never thought of it. So we force the thinking, the structured thinking. And we can have type checking, obviously, to enforce internal consistency. We can do example-based testing, think about unit tests, so we know it's sound. We can run simulations. We can run optimizations. For example, you can, in some regulations, you can elect how you want to be treated. And then there are like 20 different elections, and you wonder which combination of those is best for me. Well, you write a script and run it against Eiger, and it will tell you which are the top 5. You can run optimizations like that. And we can do property-based testing to make sure the implications we expect to be in place are in fact, in place. We get reproducibility. We get audit trails, which is really important. The head of compliance can now look at a merge request. This is completely new to them. But it gives them the power they need, because typically they look at a PDF, they go like, yeah, something like that. Then somebody else goes and implements it in Java, and then something ends up in production. And there's a huge gap in between. Now, what he sees or she sees is what's actually happening. Okay. And we can manage customization through branches, like for clients. A client needs a special treatment or special interpretation, or we can manage this through branches and keep rebasing or whatever. All right, so time for a demo. I need to quickly get my screen over here. All right, so okay. All right, so this is a demo for CBAN. It's not really important how the regulation works here. Just want to show a little bit of the code, how this looks and feels. So we have standard Haskell types to start with. What's a quarter, what's a year, reporting periods. HS stands for harmonic system. This is the code for products like aluminum and steel and stuff like that you import. So they're all encoded with those, We have countries. We have euro amounts. We make sure you cannot add euro amounts with percentages. So all the good stuff, from Haskell. Love. Okay. We have mappings, which are pure functions that explain, for example, which countries are excluded. This is the exceptions mentioned in the regulation, and which codes are, applicable under CBAN. This is incomplete the list. This is just to show how it would work. Yeah. So you go like, okay, all organic chemicals, but only some aluminiums are, in scope for the regulation. That's how you would, maybe write. These are all just pure functions, no magiciry here. But now we lift them into the Eiger context. Okay. So we have something called rules. At the top, we have the data model. For example, let me look at the supplier. This is an entity in the whole regulation. There's something called a supplier. It has a key. This is the unique key we use to identify the entity. It has a legal name, which is marked as input, which means we need this. Otherwise, we won't even start the whole machinery. And we have a country, which is marked optional, which means you may provide an input value or you may not. So supplier is very straightforward. A declarant is a little bit more complicated because we track things like how much certificates have you already bought, how much do you still need. This goes into the domain logic. It's not so important really for our understanding here. We have this one where this is a singleton, so we use this for configuration. What is the CO2 price per ton? This is just a baseline that the European Commission, specifies. Okay. And now we have, for each of those, this is a product import. Now you're actually importing something. Which class is it? How much is it? How much emissions are in there? And so on. Right? And now you have rules. So a lot of rules are declared as no rule, which means I don't know how to compute this. This means if you need this fact, you need to provide an input value for it. Otherwise, I don't know what to do. Oh, sorry, what happened? I jumped.
So a rule is an instance that.
Yeah, and Rich is going to explain that part because I'm out of my depth here. It's an instance declaration, a rule. Yeah, that's right. There's a special, yeah. And this works, there's this special type class is record. That is the entry to this, yeah. And here's, for example, an actual rule. So the certificate net is the total certificate times the price per ton minus whatever that is. What is that? That's a little bit difficult. Minus the total certificate price. Okay, so that's the rule. And that's what we mean by Excel-like. This is something something like this, without the self dot, you would put into Excel. And they can, our users can think like that. That's what they do, right? Now here, for example, it's an example for a SQL-like thing. In order to get the rate, which is the CO2 price per ton, we have this small, embedded domain-specific language that allows you, give me all rates, select from each the CO2 price per ton and sum them up, but there's only one, so the sum is actually not doing much. This gives us access to the other entities in our data space. Okay, and so on. So this is how the rules look like. And if I write them, the lawyers can read them. That's all we need. So then, for example, we have here an input JSON file. This is the key. This is the type. This is going to become important later for the instance selection at runtime. Rich is going to talk about this. And here are all the properties. There's one declarant. There's three product imports. There's the rate. These are the suppliers. And then we have a small script that calls Eiger and does a query and says, listen, I'm interested in the declarant 1, which is of kind declarant, and I want to know the CBAM certificate net. So how much overall do you owe? And if I just run this, it tells me it's 31,077 euros. Okay, that's the demo part. Richard, I think you're up. So Richard's now going to talk about the underpinning of Eiger itself. Richard.
Hi, everyone. So this is I'm just going to sort of walk through a few aspects of the implementation. There's not really time to get through everything, so I'm also happy to take questions on this part. But this will all of this code is going to end up posted. It's sort of ready to go, but I just haven't gotten the chance to click the button. It's been a busy week. But tonight, okay. So I want to walk through. I guess, or actually, before walking through, we have some design criteria as we're imagining this. What is it that we're going to have to sort of achieve with this implementation? So one is, as Alex explained, that we want to be able to compute facts by arbitrary pure functions. This should allow the full expressivity of Haskell. Generally, lawyers probably aren't going to use the full expressivity of Haskell, but if there's something complex, we want to be able to do that. Another ingredient here is that we have to take all of these facts and store them in this big heterogeneous database. We saw in the example that there were suppliers and declarants and countries and such. And so all of this has to get stored together and somehow linked up with each other. And yet, even though it has to be heterogeneous, when we're writing the library, we don't know what the types are going to be yet. The clients of Eiger are going to be the ones designing those types. So it has to work heterogeneically without even knowing the types in advance. We want to be able to track dependencies. So we might want to say, this value, the 31,000 euros, what does that depend on? What factors, what input facts might I want to change to see if there's an influence on this output? Or maybe we're working with an incomplete data set. We want to calculate something. We need to know, okay, what information from a client of the consulting company would we need to get to be able to even compute this? Right? We may not need all of the information. Maybe we just need some of the information. And we also need a way of seeding our database from an input file, such as the JSON file that we saw up there. So these are some of the design considerations. What I want to walk through today are a few of the implementation details that we see up here on the screen. Again, happy to take questions on other parts as well. So type-safe heterogeneity. So how do we store this heterogeneous set of facts in one database? So the key type is to use a dependent map. So there's a dependent map package currently maintained by Obsidian Systems, and they export a DMAP type. So this is, instead of a normal map, which is just keyed by a certain key type and a value type, we have a key type constructor and a value type constructor. So this first argument to the type is the type of keys, and then the second is the type of values. And this is the interface. So, or this is rather how we use it. So here we have a key. So you saw in the code example that a declarant has a field of type key declarant, right? It's a key to something of that type, so that when we look up that key in the database, we're going to get a declarant out. And here I've used unsafe McKey. I store a type rep, so the unsafe is really more about the int. just making sure that this key is actually unique in the database. It's not about the types. The types are fully safe here, even if you could see this constructor. A database value is something stored in the database. So this is also keyed by the type of record. Rec here stands for record, I should say. And this also stores the type rep, so that when we're doing the lookup, we can see, does the type that I'm looking up match the type that I get? And that allows us to do this without unsafe coerce. If I really wanted to trust my database, or rather not the database, if I really wanted to trust my key generation system, I could drop the type reps and use unsafe coerce instead. And then the database is just a DMAP over mapping these keys to these database values with a lookup function, as we see on the slide. Right? Given the database and a key that keys into a certain type, I might get something of that type back if that item is indeed in the database. Generally, we're always going to expect this lookup to succeed. So that's type-safe heterogeneity. It's actually not that hard to do, but I think a lot of people aren't aware that you can do tricks like this in Haskell, and it's a nice thing to be able to do. The next is maybe even a little bit more exotic. So when we're reading in a JSON file, right? If you notice, in each JSON, each sort of object in the JSON file, the first key, although first doesn't really matter because order doesn't matter in JSON, but each object contained a type field which has the type of the thing that we're loading. So what that means is that after we read in the name of the type, we have to then know a way of deserializing that type. And the classic way of doing this is using something like a from JSON instance, except that now we only learn the type at runtime. So we need a way of getting a from JSON instance at runtime. So to do that, we use a runtime instance lookup. Folks have asked about, can you just look up an instance at runtime and there's a Stack Overflow answer that says, no, you can't do that. That's impossible. It actually turns out to be quite easy. I mean, the whole implementation is on the slide. So the idea here is that we make a type edict. E stands for existential. And it's a way of taking a dictionary that is evidence that a certain class constraint is satisfied, or if you want to think about it, this is the function that actually produces something from the JSON, right? This is going to be a package around a function that produces an object from JSON. And it packs that into this data type edict. So here the constructor pack has a constraint CX. So C is a universal variable of edict. This would be something like from JSON. X is going to be the type which we will look up, something like declarant. Once we have that, then we can just build an ordinary non-dependent map, mapping strings, these are going to be the names of types, to these edicts, which are dictionaries telling you how to produce something of that type from JSON. Then I have the mci function, and the mci function takes a type rep. This describes the type for which we want to put an entry into our database, and then insert something of that type. Or it's not of that type, inserts an edict that contains the right class instance into the database. mci here just creates one, but the instance's new type has a monoid instance that allows us to combine many of these. And so we can build up our database of types for which we know how to deserialize. And then with I, given the name of the type again, we can now look up the type in our database and then get the instance back. So this is sort of the key part of the deserialization mechanism that allows us to use this JSON file to load into this heterogeneous database. The last piece I want to talk about today is dependency tracking. So this is done using the Eiger M monad, which is the monad that underlies the whole implementation. And an Eiger M is a combination of three different monadic features. It is state-like over a database. This is the database we saw a few slides ago. It is writer-like over a dependencies monoid. So we haven't seen the definition of dependencies, but you might just imagine what it does. It just sort of keeps track of what other objects and what fields from those objects that we depend on. And it's except-like over a list of errors, allowing us to abort a computation if, say, we need to compute using a fact that we don't have. So the sort of one question that has a bit of an interesting answer here is how do we get dependencies from multiple different computations? So an example of something to think about is something at the bottom of this slide here. So if I want to get, say, the total income of a person, which is going to be the sum of their earned income and their unearned income, I might have a function like this, where I read in the unearned income and then read in the earned income and then add the two. Well, what if we're missing the unearned income, right? This compute unearned is going to fail. Well, there's nothing that it can return that's sensible, because we don't have it. Yet I still want to run the compute earned action to also learn that maybe we need the earned income, maybe we don't. We can look that up as a separate lookup. So the way that we're going to do this, even though sometimes this igram is a monad, it's not an applicative, because sometimes later steps have to depend on earlier steps, although we don't see that here. So here, if we use the applicative instance using applicative do instead of a monadic do, it allows us to run both of these computations even if the first fails and accumulate more dependencies than we would otherwise. One key part of this is that the applicative instance actually needs to be non-lawful, right? If I use a monad combinator here, then after compute unearned fails, I'm going to stop and I'm never going to look at compute earned. And so that means that running this using applicative is going to give me a different result than running with monad. But that's okay, right? We're going to get more information. And so in both cases, in both applicative and monad cases, the set of dependencies we get are a subset of the true dependencies, which might need more information that we don't have. So sometimes it's okay to bend the laws a little bit. Anyway, those are the aspects that I wanted to talk about today, and Alex and I are happy to take any questions.